We already crammed off.
Okay, so welcome to this another session. This is which is really the fourth TS session in the series of interactive live sessions for the NPTEL course Applied Linear Algebra for Signal Processing, Data Analytics and Machine Learning, which is taught by the Professor Aditya Jagannathan from IIT Kanpur. So a little bit about myself. So my name is Yashvanth, and I'm presently a PhD research scholar in the fourth year under the PMRF fellowship. I'm with the Department of ECE at IISc Bangalore. So my research advisor is Professor Chandramurthy, and he's also with ECE at IISc. My broad research interests lie in statistical signal processing and wireless communication systems, whereas my current focus for my PhD thesis lies on focusing and designing algorithms for intelligent reflecting surfaces for 5G and beyond wireless communications. You can always contact me at this email ID if you are in need, and to know more about me, you can go to this website and explore for yourself. Okay, so that having set up the basic introduction about myself, the topics that I intend to cover today will be to revisit at Gaussian random variables. Basically, there were some suggestions from last time that the basics were not very clear as to how to interpret a random variable and what does it physically mean to take the covariance of two random variables. What does it mean, and how to do some problems with these kind of concepts. So I'm going to do a revisit at Gaussian random variables, and followed by that, I'm going to resume my lecture from last time by continuing on the eigen properties of matrices, and also we'll delve into positive definite matrices, which professor had covered in this week. So as usual, the first part of this particular session is going to be a quick summary of week four's lecture. So the first point is that a matrix is Hermitian if a matrix A equals A Hermitian. So what I mean by A equals A Hermitian is as follows. Suppose if I take a matrix A and it is given, it's a 2 by 2. Let's say it's a 2 by 2 complex matrix. So that is given by 2, 5 plus I, 5 minus I, and 4. Then A Hermitian is defined as the transpose of the conjugated version of the matrix A. That is, you basically conjugate, as in you take the element-wise conjugate of all the elements in the matrix A. So 2 will remain 2. Okay, so let me maybe. So 2 will remain 2. 5 plus I will become 5 minus I. 5 minus I will become 5 plus I, and 4 is same as 4. Now, once you have done the complex conjugation, then you need to take the transpose of this matrix, which means 4, which is nothing but 2, 5 minus I, 5 plus I, and 4. So if you see this matrix and this matrix A, both are same. That means A equal to A Hermitian. So this is the actual meaning of what a Hermitian matrix is. Whenever the matrix satisfies the property that is its Hermitian equals the same matrix itself, then such matrices are called Hermitian matrices. Okay, so the starting point of this week's lecture was on something called positive semi-definiteness. So any Hermitian matrix, or even this definition holds for real symmetric matrix. What do I mean by real symmetric matrices? First of all, real. What does it mean? All the entries are real numbers. There are no complex numbers. And it's a symmetric matrix. Symmetric means A equal to A transpose. Okay, here, so you can also see that A equal to A conjugate, because anyways, all entries are real in nature. And so A equals A conjugate is trivially satisfied. So real symmetric will also satisfy A equal to A Hermitian or A equal to A transpose. Both are equivalent because A conjugate is same as A. So this particular concept of positive semi-definiteness holds true for any Hermitian matrix, which can be in general complex, or a symmetric matrix, specifically real symmetric matrix. Okay, so such matrix is said to be positive semi-definite if this particular number x Hermitian Ax is positive number, that is strictly it is greater than or equal to 0 for any x in complex vector space. That is, if you see analyze the dimension of this number, what does it mean? So x Hermitian is an n-dimensional vector. So x is an n-dimensional vector. So x Hermitian is 1 cross n, and A is an n by n matrix again. So if you see here, so if you take the transpose, what does it mean? You basically exchange your rows and columns. And if I want A to be equal to A transpose or A Hermitian, that is possible only for square matrix. Okay. So the notion of Hermitian matrices, positive definiteness, positive semi-definiteness is all defined only for square matrix. Maybe I can write it here. Okay, by default, when we say it's a Hermitian matrix, at the back of our mind, we should know that it is a square matrix that we are talking about. You cannot define for a non-square matrix. Okay, so so X Hermitian is a 1 by n vector. A is an n by n matrix, and X is an n cross 1 vector. So essentially, if you compute this product, this is nothing but X Hermitian AX, which is a scalar, 1 cross 1 scalar. And I'm saying that this scalar has to be a positive number. That is, it should be greater than or equal to 0 for every x in C to the n. If this is satisfied, then this matrix A is said to be positive semi-definite. Okay. A natural extension of this definition is any Hermitian matrix or real symmetric matrix is positive definite. Note that I have removed the quantification of semi from the definition. Okay. It's said to be a positive definite matrix if X Hermitian AX is strictly greater than 0. You see here there was an equality. I'm sorry. Here there was an equality, but here that equality becomes a strict inequality. Also, I removed for this should hold for all x in C to the n except the 0 vector. Okay, because if you see if you put x equal to 0, 0 Hermitian A0, what will be? Can anyone tell me what is the answer? If x equal to 0, 0 vector, what is the left hand side? Okay, so yes, please can tell me.
If A is 0, then
No. A is not 0. Only x is 0.
0.
It should be 0, right? What is x Hermitian?
Okay.
0, 0, 0, 0, something. Now there is a matrix A.
Yes.
Times this is nothing but again 0, 0, 0, all 0. So no matter what the A is, these zeros will kill the entire product and become 0 only. Okay. So LHS will become 0 only if x is 0. But saying that 0 is greater than 0 is meaningless. That's why when we talk about definiteness, when we talk about strict inequality, you should not include x equal to 0 case. Is that clear? Okay, I hope it's clear. Okay, now having defined what Ph.D and Ph.D matrices are, here are the short properties which professor had alluded to in the class. Number one is the eigenvalue property. That is, for a Ph.D stands for positive semi-definite. Okay, and Ph.D likewise stands for positive definite. Okay, so that means underlying assumption is that they are already Hermitian matrices. Okay, for a Ph.D matrices, the eigenvalues, that is lambda 1 and so on to lambda n, if it's an n by n matrix, are strictly non-negative. That is, they are greater than or equal to 0. In other words, for a PD matrix, all the eigenvalues are strictly greater than 0. So again, the only difference between PD and PSD is here is the equality sign, here there is no equality sign. Okay, that is the first property. Second property, what professor had proved in classes, eigenvectors corresponding to distinct eigenvalues are orthogonal. Just a minute. Yeah, I'm back. So eigenvectors corresponding to distinct eigenvalues are orthogonal. This is the second property which professor had taught in the class. And third property which professor had done is you can always show that any matrix, any PSD matrix or PD matrix A can be decomposed as U lambda U Hermitian. You remember last time when we defined eigenvalue decomposition, we saw U inverse. Now that has become U Hermitian. Okay, for a PD matrix, you can always have a Hermitian kind of operation for the last this matrix. So u lambda u Hermitian, where u is the collection of all the eigenvectors as the column vectors. Lambda is a diagonal matrix with all the eigenvalues as the diagonal, and u Hermitian is again the Hermitian of the matrix with all eigenvectors. Okay, this is also called as spectral decomposition of a Hermitian matrix or a positive semi-definite matrix. Now, related to this is the Cholesky factorization.
One question.
Yes.
Regarding this statement saying that eigenvectors corresponding to distinct eigenvalues are orthogonal.
Mm-hmm.
So, is it also possible that all the eigenvectors, they follow in the same basis line, right? In that case, they will not be orthogonal.
Okay, so basically the catch here is you should so yeah, I mean, so what you're trying to say is you can all if I'm given an eigenvector x, then c times x is also another eigenvector. Then you're arguing that cx and x they're not orthogonal, correct? Is that what you're
Yeah,
saying?
yeah.
So what you should ideally, so if you remember, x is a eigenvector for lambda with the eigenvalue. Now c times x is an eigenvector with the same eigenvalue. See, this is possible only if the lambda is same. But now what I'm saying is distinct eigenvalues, which means if I have lambda 1, lambda 2, and if lambda 1 has x as eigenvector and lambda 2 has y as eigenvector, it is not possible to write y as c into x. That's what this property says. Is that fine? So essentially, I'm trying to say that, I mean, that particular statement was for a given eigenvalue, you can find two eigenvectors, two different eigenvectors. But here I'm saying distinct eigenvalues, means the eigenvalues themselves are different. Is that fine? Yeah, I'm not able to hear the response. So I hope it's fine.
You're answering a question, sir, right?
Yeah. I just told the answer. Someone asked me, how
Okay.
can x and cx be orthogonal? For example, if you take x is equal to x, let's say x1 is equal to some vector x, okay, and x2 is equal to some other vector c times x, then you can know that x1 Hermitian x2 is nothing but c times x1 Hermitian x1, which is not equal to 0. That is absolutely true, but the underlying assumption was that x and cx can become the eigenvector only if the eigenvalues are same. Both vectors x and cx correspond to same eigenvalue lambda. But here I'm talking about distinct eigenvalues.
Okay, yeah.
Yeah, thanks. Yeah.
Yeah, thank you.
So now the next thing is Cholesky factorization. That is, which says that any Ph.D matrix or PD matrix can be decomposed as A equal to GG Hermitian. Okay, you can just write as product of two matrices G times G Hermitian, where one way to compute G is take this particular U matrix, multiply this with the square root matrix of this. That is, basically take the square root of every element of the diagonal matrix, and then call that as lambda half, multiply both these matrices, that will give G. Okay. Now, for example, you can verify G Hermitian is nothing but U lambda Hermitian U Hermitian. Okay, but okay, maybe I will write it. Okay, so then A equal to GG Hermitian equal to U lambda Hermitian into U lambda per half times Hermitian, same as U lambda Hermitian into lambda h by 2 into U Hermitian. But you see, remember, all these eigenvalues are positive. That they are positive real numbers. Okay, that was the that was our initial statement. That means if you take the Hermitian of this matrix, it will still be the same itself, because it's all, after all are real numbers, and diagonal elements will still remain the diagonal elements, which means your lambda power h by 2 will remain as lambda power half itself, u into lambda half into lambda half into u Hermitian. This is same as u lambda u Hermitian, which is our original spectral decomposition. Okay, so one way to compute the Cholesky factor is just do the eigenvalue decomposition u lambda u Hermitian, find the square root of the lambda matrix, meaning that you take the element-wise square root of all the elements, and then pre-multiply that square root matrix with U matrix. That will give the G matrix or the Cholesky factor. There are applications of Cholesky factor in uncorrelating the correlated data, in correlating the uncorrelated data, and so on. So this is what professor had taught in class. For example, if there is a Gaussian random vector Z, which is normally Gaussian with zero mean and covariance matrix R, okay, then define another random vector Z prime as R power minus half. That is, you take the square root of R and invert it. Okay, times Z, which is your original Gaussian random vector with mean 0 and covariance R. Then you can show that the resultant vector Z prime is also Gaussian random vector with mean 0, but covariance matrix is I. Okay, it's no more R. So basically, if you remember what is R, R is some covariance matrix. But if you say I, that means I have uncorrelated all of them because it has become a proper diagonal matrix now. Okay, and with what is this R half? R half is precisely the Cholesky factor of the matrix R. I mean, so basically you can show that Cholesky factor of matrix A is same as A power half. I mean, people generally call square root of a matrix as a Cholesky factor itself. Here it is not exactly Cholesky factor, it is inverse of Cholesky factor. Okay, if you multiply by such kind of matrix, the resultant matrix is such that you will get a diagonal covariance matrix, meaning that I have uncorrelated the entries from a correlated entry. Okay, similarly, on the other hand, if I have an uncorrelated data given in hand, okay, then if I compute the random vector Z prime equal to R power half times Z, and the resultant matrix will be such that it is Gaussian distributed with mean 0 and covariance R. So you have somewhat converted data which had an identity covariance, it is a diagonal covariance matrix, to a general covariance matrix which need not be diagonal, meaning that you have correlated on a set of uncorrelated data. Again, the operating linear transform that you need to apply is again R. Here is the Cholesky factor itself. Okay. So then the next topic was principal component analysis. Essentially, the goal of the principal component analysis is to reduce the high dimensional data into low dimensional data. For example, if let's say there are d data points, x1, x2, and so on till xd, and each of them is an n-dimensional vector. Okay, this is an n cross 1 vector, this is another n cross 1 vector, this is another n cross 1 vector. There are d such n cross 1 vectors. Okay, d n-dimensional data points. Okay, each point, if you remember the first class, I told each point in the space, coordinate space, can be represented by a vector. So each point here is a data point. This is a data point in the n-dimensional space. Okay, that's why it is an n-length vector. Now, then you can show that the best n-dimensional representation, the best m-dimensional representation of these vectors, these n-dimensional vectors given by these d other vectors, v1, v2, and so on till vd, which are basically transformed versions of every individual vector. So basically, you take the first vector x1, transform it, but this pre-multiplied by this matrix V Hermitian, you get the V1. And so on till every vector you do the same thing. You get VD. And such that the dimension of this V is given by m cross 1. This was n cross 1. This n cross 1 such that m is much less than n. Okay, you have somehow representing the same data point with another representation whose length is very much less than the original dimension of the vector. This is precisely the goal of principal component analysis. Now, if I give you the vector V, okay, and if I give you the matrix capital V, I can always reconstruct my original vector. That is, if I'm given a vector x, okay, and I make a transformation by V Hermitian, I get V1. Now what I will do is, instead of digitally storing x1, I will store V1 vector in the memory. Now, if I want to retrieve the actual vector x1, what I do is I take the V1, do a V itself. So basically, you undo the operation. That is, instead of doing V, if you take V inverse Hermitian on both sides. Okay, this will become identity, which means x1 is nothing but V inverse Hermitian times V1. So take the vector V1, do this operation, you get back the original vector x1. So essentially what it amounts to say is, instead of having to store x1, x2 and so on till xd, just store v1, v2 and so on till vd and the matrix V. If you store these entries, you can uniquely reconstruct x1 and so on till xd. Okay, if you see the memory requirement for storing vi vectors and the matrix V, the memory requirement is much less than the memory for the original vectors x1 till xt. Okay, that is the usefulness of a principal component analysis. That is, these are the matrix V will describe what are the principal components along which you want to represent each of these d data points into a low dimensional data points. Okay, and how to construct this V matrix? It is in fact is a matrix of first m eigenvectors of the sample covariance matrix. Okay, that is sample covariance matrix is defined as this particular expression. Xi is a vector, mu I is a vector, xi is a vector, mu is a vector. So it's an n by 1, n by 1, 1 by n and 1 by n. So totally is an n by n matrix. So for this n by n matrix, you can show that this is a Hermitian matrix. Okay, please note down this fact that any covariance matrix is Hermitian. Why? Just take the transposition of this particular vector. What happens? This guy will come first and this guy will go behind with the Hermitian. You can show that this again turns out to be xi into xi minus mu Hermitian only, same as this guy. Which means any covariance matrix is always a Hermitian matrix. Okay, so essentially what you do is, when you're given the vector x1 till xd, just compute this covariance matrix where mu I is the mean of all the vectors. Okay, just compute the sample covariance matrix and then compute the eigenvector, that is represent R is equal to u lambda u Hermitian. Take the matrix U and take the first m columns. Okay, that is, if I want to represent my n-dimensional vector as an m-dimensional vector, take the first m columns of the matrix U. Okay, and then take the Hermitian of it and multiply with all the x's. This is the procedure. Okay, some application of using this kind of an approach is to do a facial recognition, where you have a database of initial images, and when you are given another test image to recognize which image is this, you take this principal component, and in the principal component domain, you basically compare the given test data with each of the eigenfaces. And then you say, you measure distance, you measure something called the distance between two images and select that particular image which has the least distance. Right? So this is what professor had taught in the class. So are there any doubts? If there are any doubts, you can ask now. Otherwise, I will.
Yeah,
Yes.
I have. So in this procedure, we had a vector x of n dimension, right?
Yeah.
So now you calculated R. In R, when we calculate R, this is only going till D, right? This is till D dimension, which is the reduced dimension.
No. R is still an n by n matrix.
But
why? Because see, this is an n by 1 vector. Mu I is an n by 1 vector, correct? Because see, mu I is defined as sum over all xi, which is again going to be an n by 1 vector.
Okay, then why you put this summation from 1 to D?
That's because that is how, see, okay, so I have to then explain this. So how is covariance? Maybe I will, okay, that's a good question actually. So if you see covariance matrix, okay, of a vector x. Okay, it's called it's this defined as expectation of x minus mu into x minus mu Hermitian. This is correct? Is this correct?
Yes.
Okay. Now, what is really expectation? Expectation is really the mean, right? That means I need to take the average of all these quantities. So what I have is I have x1, x2, and so on till xd, and correspondingly I have So there is one small mistake in the sense that there is no mu I. It's just one mu. Okay, now it's fine. So if you see, I have x1, x2, and so on till xd. These are the d data points. Now I want to take the average of all these things, all these vectors. That will basically approximate the expectation, because expectation is nothing but the mean of the random variables. And mean is what? If I give you x1, x2, and so on xd, mean is nothing but 1 by d summation xi, right?
Yeah.
That is exactly what I'm doing here. Here it is not mean of just xi, it is mean of this product x minus mu into x minus mu Hermitian. And that's what I'm doing here.
Okay, so we wanted to look at this principal component. So D are the principal components, right?
Now, D are not the principal components. The m eigenvectors of V, of this R, are the principal components, PCs. Because I'm taking these are D data points. Okay, I'm projecting each of these data points onto some matrix V, and I'm getting the low dimensional data points D. You see, input is D data points, output is also D data points. The only difference is the length of the data point is now changed.
The input is D, output is also D, right? In this, whatever.
D data points. D vectors are the input vectors, and D vectors are the output vectors also. The only difference is each vector, the input vector had n length vector, but the output vector has m length vector, where m is much less than n.
Okay, got it. Yeah.
Okay, so this is called principal component analysis. And what are the principal components? These are precisely the m eigenvectors. That is, you choose the matrix V to be the first m eigenvectors of the matrix R, right? These m eigenvectors are called principal components because you only essentially take those contributions from these vectors and represent them in the low dimensional data.
Yeah, and in this example, where was those eigenvectors computed, or we didn't?
So we just told we need to compute. Once you figure out what this matrix R is, you need to compute the eigenvectors and eigenvalues for this matrix R. And then you need to pick the best first m eigenvectors.
Okay, thank you.
Yeah. Okay, great. So the agenda for today is basically to quickly revisit at Gaussian random variables, because I think last time we had some suggestions to look at some basics of random variables. So for the next 15 to 20 minutes, for those of you who are not very familiar with random variables and probability theory, I'll quickly go over the basics so that whatever is required for this course, I will cover all the basics in just next 15 to 20 minutes. Okay. So the first question is really not a question, but it's just a topic of revisiting random variables. Okay. So first thing is basically to understand the notion of probability. Essentially the random variable theory comes in probability theory. So we will first understand what probability is. So let me write down some definitions and let me write down some small notes so that people can understand the development of what a random variable really is. Okay. Now, if you consider an experiment whose outcome, okay, you do an experiment and you get an outcome, or it's also a result for some people. It can be an experiment whose outcome or result can be predicted with certainty. That is, you can certainly say what is the result of a particular experiment. Okay, such kind of experiments are called is called a deterministic experiment. Okay. What is an example is, now if you apply let's say a potential difference, for people who are familiar, I mean almost all of us know from our high school, potential difference is also called voltage, for very very informally. Potential difference equal to E volt, let's say, between two ends of a conductor, okay, which means it just conducts current. And if resistance equal to R, then its current, that is the current flowing to the conductor, is deterministically calculated. It's deterministically calculated as I equal to E by R. Correct? This is nothing but our famous Ohm's law. So what it says is, if I suppose I'm going to perform an experiment and I know, in prior, that is before, if I know before even doing the experiment that I'm going to, let's say, give a potential difference of 5 volts and the resistance is equal to 1 ohm, then even before conducting the experiment, even before seeing the result, I will know that the result will be equal to 5 ampere of current. 5 divided by 1 equal to 5. That's such its type of experiments are called deterministic experiments. Okay. On the other hand, okay, so just hold on. I'm getting a kind of call. Just hold on. Okay. Yeah. Am I audible? Hello. Am I audible? Can anyone confirm?
Yes, sir.
Okay.
Yes, sir.
Yeah. Thanks. Yeah. So now an experiment. Okay. Now we have seen what a deterministic experiment is. Now an experiment where the outcome of a particular trial of an experiment cannot be predicted is called a random experiment. So we saw what a deterministic experiment is. That is, if you can predict what the outcome of the experiment is going to be, that's called a deterministic experiment. But if you cannot predict the outcome, that is outcome of a particular experiment, unless you do the experiment and see what the result is, you will not be able to know what the result is in prior. Such kind of experiments are called random experiments. A simple example is tossing a coin once. Okay, I know that if I toss a coin once, it will either be head or a tail, but I will not be able to tell for sure whether it will be a head or it will be a tail. Unless I toss and see the coin, I cannot tell. Only if after tossing, I will know whether it's a head or a tail. Again, if I toss the second time, that particular result could be different from the first. For example, first time I can get a head. Second time I can get a tail also. I can get a head also, right? So every time you perform the experiment, still the result of that particular experiment cannot be predicted. Okay, such kind of outcome cannot be predicted. Such kind of experiments are called random experiment. Okay, so now related to the random experiment, the notion of sample space is as follows. Okay, it's a set. Okay, it's denoted as a capital omega. It's defined as the set of all possible outcomes of an experiment. Okay, so for example, in above example, if I toss a coin, what is the sample space? Can anyone tell me? It is set of all possible outcomes. Can anyone tell me what is the set? What is the sample space for this experiment tossing a coin?
2.
Yeah, it's not. That is a number of possible outcomes. I'm asking what are the outcomes itself? Nothing but two things.
Yeah.
The
Head
outcome
or tail.
exactly. It's either a head or a tail.
Or tail.
Okay, so I can represent it shortly as H comma T. H means head, T means tail. So this omega is really it is a set with two elements, H and T. Means the outcome can either be a head or it can either be a tail. Okay, that is called a sample space. So remember, sample space is for a random experiment. Deterministic experiment, there is nothing as such as this particular notion of sample space, because you already know what the outcome is. There is nothing like set of all outcomes. You know the outcome already. Okay. Now, in this particular random experiment premise, next the event. It's called E. Okay. Event is a subset of the sample space. Okay, that is called an event. So, for example, if I'm interested in the event that I want only heads to occur, okay, that is a particular event. For example, H. It's a subset of this particular set HT, right? Therefore, this H is an event. Okay. Now comes the probability. Probability of an event. Probability is defined only for an event. Okay. Of an event. E. Because event is denoted by E, right? Equal to this probability is denoted as P of E, equal to number of favorable outcomes in E divided by total number of outcomes, right? So that is nothing but it's exactly given by cardinality of the set E divided by cardinality of set omega. Okay, that is the number of elements in the set E divided by number of elements in the set omega. Whatever this ratio gives is called the probability of that particular event. And for every event, you have a number, you have a probability. So probability of any event is a number, okay, is a number between 0 and 1. Okay, because at most, since E is a subset of omega, at most it can be the omega itself, because any set is a subset of itself. Okay, which is equal to 1. And it's possible that null set is also a subset of omega. So it's possible that is equal to null's cardinality of null set divided by omega. This is something but 0. This is something but equal to 1. So probability of any event is a number between 0 and 1. Okay. Now let's take an example. Okay. So let's now consider another different example of rolling a die. You know, we all know a die, right? We all play in Ludo and everything, snake and ladder and so on. So there's a die and it has 6 faces. and each face is equally likely to appear. Okay, then clearly this is a random experiment. Why? Because I should roll a die once, because I know that any one of the 6 faces can come, but I don't know which face will exactly come. So unless I roll the die and see the outcome, I cannot know. No one can tell what the outcome is going to be. So that's a random experiment. Okay. So in this context, question 1 is find the probability that the number 5 will appear. Okay, that means what I'm asking is, okay, any of the 6 numbers can come, but I'm interested in the event that 5 should appear. That is, I want what is the chances, or probability is nothing but chance. What is the chance that a number 5 will appear if I roll a die? Okay, then for the answer is as follows. So I'm interested in knowing when will 5 appear. Okay, so first let's write on the sample space. So sample space is independent of what we want to know. Sample space is a set of all possible outcomes. So what is sample space? Can anyone tell me what is the sample space for this experiment of rolling a die?
1, 2, 3, 4, 5, 6.
Correct. So it's a good 1, 2, 3, 4, 5, 6. Perfect. Now, first question is, what is the probability the number 5 will appear? That means I'm interested in 5, appearance of 5. That means my event of interest is just this. Is this clear? I'm only considering the event and number 5 should come. Okay. Now, what is P of E? Cardinality of E divided by cardinal of omega. What is it? Can anyone tell me?
1 by 6.
Correct. It's 1 by 6. What does it mean? Intuitively, physically, what it means? The probability of occurrence of 5 is equal to 1 by 6. That is correct, right? Because with the chance that 1 by 1 time out of a 6 times I roll a die, I may get a 5 number. With other probability, I may get any other number other than 5. Okay. Now the next question is, find probability that an even number will appear. That is, if I roll a die, then what is the probability that an even number will appear? Now the omega will remain the same because that is the total collection of all possible outcomes. Now, can anyone tell me what is the event that I'm looking for? Event.
Even number. 2, 4, 6.
Correct. 2, 4, 6. Okay. So then what is the probability of this occurrence?
3 by 6. 1 by 2.
Correct. Equal to 3 by 6, which is equal to 1 by 2. This again, it makes intuitive sense because the number of even numbers is exactly equal to number of odd numbers from 1 to 6, which means with half probability, half of the times I will get an even number, and other half of the time, if I roll a die, I will get an odd number. Okay, that's how you should think about probability. Probability, one aspect of probability is mathematically doing these kind of calculations. The other angle, intuitively you need to think, okay, what is the chance that if I roll a die of 6 numbers and every face will appear equally likely, then what is the probability of getting an even number? We should intuitively think that it should be half, because half the time even number will come, other half the time odd numbers will come. Okay, that's how you need to build the intuition of probability. Similarly, to complete this chain, we'll find the probability that a prime number appears. Prime numbers, for those of you who are not familiar, it has a definition that two numbers are said to be prime if there is no common factor between them except the number 1. Okay, so maybe for those of you who don't know what are prime numbers, I will tell you that E is equal to 2, 3, and 5 other prime numbers from the set of 1 to 6. Okay, so that implies that probability of E is equal to, again, 3 by 6 equal to half. Means with half probability you'll get a prime number. with other half probability, you won't get a prime number. Okay. Is this clear? Please ask me doubt if right here on what is probability, how to compute probability of different events. Okay, so I think this is clear. Now comes the notion of what is called a random variable. Okay, so now in general, the outcome needn't be a number. For example, if you toss a coin, you get a head or a tail. They are not numbers. But if you roll a die, you get a number 1, 2, 3, 4, 5, 6. That's perfectly fine. The outcomes are numbers themselves. But every experiment will not be such that the outcome should be a number. Okay. So in general, outcome need not be a number. Okay. Therefore, it's only for mathematical calculation. Okay. Ease of mathematical calculations. We map every outcome of omega, that is sample space, to a real number. The resultant mapping is called a random variable. Okay, so what I mean is, example, let's say just consider a simple example of tossing a coin. Okay, toss a coin, which means a set omega will have only 2 points, h and t, but they are not numbers. So what you do, you take a real line, that is your x-axis, for want of a better name, map both these outcomes to some number on real number. For example, let it be 0, for example, and call this as 1. Maybe I'll use a different color. Okay, so whenever I say that I get a 0, that means it implicitly means that I'm saying that I got a tail by a toss of a coin. When I say that I am getting a 1, that means I'm getting a head. This mapping of any outcome of an experiment to some number, real number on the real line, is called, this mapping is called as a random variable. Because now the resultant, you can actually tell that instead of saying the outcome is either h or t, you can now say that the random variable takes a value either 0 or 1. Okay, so essentially what happens is probability of the event h. Okay, that is, what is the probability that a head will appear? That is called probability of event h, is same as the probability that the random variable takes a value 0. It is same as half. Similarly, the probability of the tail, occurrence of tail, is same as the probability that the random variable x will take a number 1, is same as half. Okay, is this clear? Random variable is just a kind of a placeholder for any particular outcome in the sample space. Is that fine? So if I really say what is the probability that a random variable takes a number, let's say 0, that means implicitly I'm asking what is the probability that the event is event associated is a head event. Okay, and who decides the mapping? You can define your own mapping. Where how should t be? Who told that t should be mapped to 0 and h should be mapped to 1? No problem. You can map it to any number, because anyway the probability is what is more important to us. And since there is a 1-to-1 mapping between the event space and the the real line, the probabilities values are going to be same regardless. Okay, so this is what is a random variable. So random variable is just the mapping of every particular outcome of the sample space to a number on real line. Okay, so this is what is a random variable. So going forward, random variable will also be a random experiment. Why? Because this random variable can take either 0 or 1. Okay, now if you see the set of all possible values the random variable x can take, So let me call omega x. So think about 0 or 1. Is this clear? If when to obtain a 0? Whenever I obtain a tail in the original event space. When to obtain the number 1? Whenever I obtain a number head in the original event space. Okay. So now the random variable also will have a random. You cannot predict what the value the random variable will take. That really depends on what the actual result of the experiment is. Okay. So if you have doubts in random variables, please stop me now itself. Okay. Now let me talk about types of random variables. First is called discrete random variable. Okay. Here in discrete random variable, the random variable x can take only a finite number of values. Or to be more mathematically precise, countably infinite. Maybe if you don't understand what countably infinite is, just ignore for now. Just think this particular kind of random variable that it takes finite number of values. For example, here this is a finite random variable. It takes only two values, 0 and 1, depending on whether head or tail appears. Okay. All right. Now, example, you can go and refer back, but it's okay. I'll just mention the example, but I will not tell what these are really. Binomial random variable, Poisson random variable, and so on. Okay. The next type of random variable is called continuous random variable. So now you should have guessed what continuous random variable mean. If discrete says it should only take finite number of values, then here x can take uncountably infinite values. Or that is, in other words, you can say that x can take values in any interval on real line. Okay. Now, precisely the example for such random variable is the Gaussian random variable, which we have been looking since the last class. Okay. So if you remember what was Gaussian random variable, recall x is Gaussian with PDF. We sold something called probability density function, right? I will tell what PDF means also today. With PDF equal to 1 by root 2 pi sigma square e power minus x minus mu the whole square by 2 sigma square. And what was the range of x? X was from minus infinity to plus infinity, the entire real line. Every point in real line can be realized by this kind of random variable. If a random variable is Gaussian, then this random variable can take any point on real line, okay, with some probability. So for example, here in this example, the random variable x can take values between 0 or 1. It takes a value 0 with probability half. That is, half the time it takes a value 0, and other half the time it takes the value 1. But here it takes the value of any number with some probability. We will see how to compute that probability with which a Gaussian random variable can take a particular number or a particular interval on the real line. Okay, so this Gaussian random variable comes under the class of continuous random variables. Then the natural question is, what is a probability density function? That is, what is PDF? Okay, its PDF is defined for continuous random variables only, and so it is defined even for Gaussian random variables. So PDF is used to define the random variables. So RV means random variable. The random variable's probability coming within a distinct range of values. That is, if I want to characterize, for example, continuous random variable, let's say Gaussian random variable. If I want to characterize what is the probability that this random variable X will take a value between, let's say, A and B. Okay, that is what I'm saying is, let's say this is a real line. Okay, this is a real line. And let's say this is A and this is B. What is the probability that your random variable will take the line? It will take, the random variable will assume this random variable X will take a point, a number in this interval. What is the probability? What is the probability that X belongs to the interval A, B? To answer these kind of questions in a range of values, right? It's a range of value from A to B. So there are so many numbers in between the interval A to B. How to compute these kind of probability? It is computed using the probability density function. That's what. So probability density function is used to define the random variables probability which are coming within a distinct range of values. Okay. That is so the way to mathematically represent is probability that X lies between A and B is given by integral A to B fx of x dx. The subscript x stands for the random variable, that is x, the random variable. The small x stands for the integration variable. The argument stands for integration variable. Okay, this is how we define this. This fx of x is a PDF of x. So the real utility of PDF is to compute the probability of the random variable in a given range. Okay. Example for a Gaussian random variable. What is the PDF x of fx of x is nothing but if you draw the graph, I'm directly drawing the graph. Okay. It will be something like this. Okay. The first question is, what is the probability that the random variable x takes a value greater than or equal to 1? Okay. That is where x is Gaussian random variable with mean, let's say 1 and variance 3. So these notations, please refer the previous class. We have defined what does this notation mean. Means it's x is a Gaussian random variable with mean 1 and variance 3. And we have defined what mean, variance, and everything in the last class. So if I want to compute this, what is the definition? This is nothing but 1 to infinity, because x can go as large as infinity. That is my, if you see the Gaussian random variable, it can go up to infinity. So 1 to infinity fx of x dx. So what does it mean? 1 to infinity 1 by root 2 pi into 3, because sigma square variance is 3, into e power minus x minus 1, because variance is mean is 1, the whole square, by 2 into 3 dx. So see, it's this particular guy is a function of, this particular guy is a function of only x. So just integrate with respect to dx and take the limit from 1 to infinity. Whatever number comes out to be, that is the probability that x will take a number which is greater than or equal to 1. Okay. So pictorially, I'm asking, if this is my probability density function, so what is this integral a to b fx of x dx? It's the area under the curve PDF in the range a to b. So I'm pictorially asking, you fix 1 here. What is this area? That's what I'm asking. If you compute this area, that gives a probability that the random variable will take a value greater than 1. So essentially, PDF can be thought of as some kind of antiderivative of the probability itself. Okay. And the second question is a CDF. This also we defined in the last class. called the cumulative distribution function. Okay, so what is cumulative distribution function? It's defined as capital Fx of x. Okay, you see here small fx of x is some function. It's a PDF, but when you write capital F, that means it's a CDF. CDF is really given to the probability that the random variable x will take a number less than small x, where small x is same as this number. Maybe I will write this as rho. Okay, then this becomes rho. Okay, this is a function of rho. And this is precisely the definition of CDF. Okay, for a Gaussian random variable, this is nothing but minus infinity to rho fx of x dx. Okay, suppose x is normal 0, 1, that is Gaussian 0 and 1. Then what is your CDF? Fx of x is nothing but minus infinity to x 1 by root 2 pi e power minus x square by 2. Correct, because mean is 0 and variance is 1 dx. Now this particular integral is numerically, very well tractable. Mathematicians have called this particular integral as phi of x. It's a standard integral called phi of x, and it's also given by 1 minus q of x. This is called a q function. Maybe you can always find a handbook of mathematics, and you can find a list of tables. One of these tables is list of q function. Okay, it's a this integral is not very easy to solve. So what they do is they directly numerically evaluate this integral and give a list of tables for every value of x. What is the integration value? Okay, so this is called q from 1 minus q of x, or it's also called phi of x. Okay, so this is your final answer can be represented just by this particular number. What is phi of x? Where x is this. Okay, both are same. Fine. So now let me do one small question, and then we will take some break, and then we'll resume back with solving one particular question, I think very related to previous assignment, and then we will look at some eigenvalue properties. Okay, so let me solve one question. Let x be normal mu comma sigma square, Gaussian with Gaussian random variable with mean mu and variance sigma square. Find CDF of x in terms of phi of x. That is, I'm saying arbitrary mu, arbitrary mean, and arbitrary variance. And the question is, what is the CDF of? How will you compute the CDF? CDF is a number, because probability. CDF is equal to probability. It's a number. It's a number. So all I'm asking is, what is number as a function of row? For every row, you have a number. That's how you need to think about it. So the question is, for a given x, what is the CDF of this random variable x, which is Gaussian with mean mu and variance sigma square? So solution, I will give you a fact. You can verify it very easily. If there is a random variable x which is with Gaussian mean 0 and variance 1, then the random variable x dash defined as some a times x, where a is any scalar, is also Gaussian distributed with mean given by a times the mean of the original random variable, which is 0, and the variance a square times the original variance, that is 1, which is same as n of 0 comma 1, 0 comma a square. Similarly, then x double prime defined as b plus x is also normal with mean given by b plus the original mean 0, and variance is unchanged, it is 1. Okay, variance is unchanged if you add a constant. Okay, these are the two facts. Okay, now with this, what is my fx of x? That is my CDF equal to probability that x is less than or equal to small x. Okay, this is the same as just subtract mu on both sides. Then divide by sigma on both sides. Okay, let y be the random variable x minus mu by sigma. Okay, then this is not just naming as asking probability that y is less than or equal to x minus mu by sigma. Okay, now claim if x is a normal mean of mu and sigma square, then x minus y, which is equal to the random variable x minus mu by sigma, is also Gaussian, that is with mean 0 and variance 1. Okay, why is this true? Very simple. So if x is n of mu comma sigma square, implies x minus mu is, see, if I subtract, only the mean will get subtracted. The variance will remain unchanged. So mean will be, it will be normal. I'm subtracting by mu. So mu minus mu is 0 comma sigma square. And implies x minus mu by sigma is normal 0 by sigma comma sigma square by sigma square. Because if I scale by a, the variance will scale by a square. But 0 by sigma is same as 0 and sigma square by sigma square is 1. So if x is random Gaussian with mean mu and variance sigma square, then x minus mu by sigma, this random variable is Gaussian with mean 0 and variance 1. Now can anyone tell me what is the probability of y less than or equal to x minus mu by sigma, where y is n01? So see this, I told that if the CDF x is n0c1, n of 0 comma 1, then the CDF is given by phi of x, where x is the value at which I'm computing the CDF. Can now anyone tell me what is this? Now here y is the Gaussian random variable with mean mean equal to 0 and variance equal to 1. Okay, what is this in terms of phi? Yes, can anyone tell me? Nothing but phi of x minus mu by sigma. That's all. This is the value at which I evaluate the CDF, input to CDF function, right? So that is going to be the argument of phi function. Is this clear? Please, can anyone confirm if this is clear? Okay, I hope this is clear. If not, please stop me. So essentially what I'm trying to say is, conclusion, if x is normal mu comma sigma square with mean mu and variance sigma square, then fx of rho, that is the CDF, is given by phi of rho minus mu by sigma square. Now, once you, that is what I'm trying to say is, for a given rho, compute the number rho minus mu by sigma, not sigma square, sigma. Okay, and then look at the standard tables, phi of this number, whatever the number gives, that is the CDF of this random variable x. Okay. Okay, so now it's 7:10. We will take a 5-minute break and then we will resume from this point. Okay, so we'll resume now. Can anyone confirm if I'm audible?
Yes, sir, audible.
Yeah, thanks. So, okay, the last topic that I would like to cover in this random variable theory, the notion of covariance or correlation between two random variables. Okay, so the setting is as like this. Suppose we have two random variables, x and y. Okay, then the correlation between x and y. So correlation is defined between two random variables. Okay, the correlation between x and y describes the knowledge of the value taken by random variable y when the value taken by x is known. That is, so we know that, so let's say there are two random variables x and y. So again, we know that without really performing the experiments, you will not know what are the values that these two random variables take. But now suppose if I know what the value, the value of the random variable x, the value that it has assumed, and now without really having to perform the experiment to know the value of y, just by knowing the value of x, can I predict the value that the random variable y will take? That particular behavior of getting the knowledge of the random value taken by the random variable y when the value taken by x is known to you, that particular predictive nature that you can have inherent between these two random variables is called the correlation between x and y. That is, if I'm able to complete, so let's say an example where the random variable x represents the event that I'm interested in getting an even number when you roll a die. Then the random variable will take a value 2, 4, or 6. Now, if I'm interested in another simultaneous event, what is the event that I will get a 1 when I roll a die? Right? Now, if I know that x is denoting that particular event of getting an even number and y is denoting that particular event of getting a number 1, if I know that x has given 2, 4, or 6, then definitely I know that 1 has not occurred. Which means even before y, I want to estimate, or I want to see what the value of y is. I can tell what the value of y will be. I can predict what the value of y will be just by knowing what the x, the value of y that x has assumed. This is called the correlation between two random variables. Okay. For example, roll a die. Okay. So omega is equal to 1, 2, 3, 4, 5, 6. First, this event that we get even number. Okay. Then what are the values? Y is equal to 2, 4, and 6. Consider simultaneous event that we get 1. Okay. Now, if y equal to 2, 4, that is z equal to 1, just one event. If y equal to 2, 4, and 6, that means I know that only one of these numbers have occurred. Either one of the even numbers have occurred. That means I know that z cannot be equal to 1. Else if y equal to 1, 3, and 5 implies that z equal to 1. Right? That means y and z are correlated. Okay.
One question.
Yes.
Is this understanding correct that in this example we saw there is single random variable process and we are evaluating two random variables from the single random process? Should it not be that we have two separate random variables and they have their own random variables and then we do a correlation against each of them?
So there are two things to it. So it is not really a random process that we are considering. So if you because random process is something different, okay, that is different from what we are talking here. So that also has an additional dimension of maybe it's called a time or an index set, whatever you call. But whatever you alluded to, that you have two different random variables and then you want to compare both of them, that is in some sense correct. But I'm not going to something in depth because there's something called probability space. Okay, so that is little tricky to understand. So if any probability can be, theory is revolves around a triplet called probability space, which is given by sample space, the collection of all events, and a probability measure. This triplet will always be, it is the underlying triplet that is defined on any particular probability framework. From this, you take two random variables, let's say x and y. You define up under, so how will these x and y are obtained? Under appropriate mapping. If you remember, I told that there is a mapping that you take from sample space to the real line. That is under your control. You can define your mapping on your own. Under different mapping conditions, you get different random variables x and y. And then you compare between these two x and y, and then talk about correlation and so on. Is that okay?
Yeah, got it. But in this example, we are taking a simplified case where the random variable belong to the same variable actually.
Correct. You're right. Yeah.
Okay, thank you.
Yeah. But for those of you who didn't understand what I spoke here, just forget about it. It's an actual more mathematical way to, talk about probability. In today's lecture, I have simplified almost many things, so that just you understand what is some basics of it. Okay. So basically, the correlation means by knowing what one random variable is, can you tell me the value the another random variable will take? So that particular nature is called correlation. Okay, if you cannot give such knowledge, that is, if knowing one random variable, that is knowing the value of one random variable, if it does not give any knowledge of the other random variable, then these random variables are uncorrelated. Okay, means they are not all correlated. X and Y will not tell anything about each other. X can be anything, Y can be anything. Okay, for example, if I toss a coin 2 times, okay, if I denote the random variable, what is the event that a head occurs in the first trial, and if I denote another random variable Y, which denotes the event of occurrence of a head in the second trial, okay, these two random variables will not be correlated. In the sense, if I know that the first time I have got a head, it will not tell you anything about in the second time whether I'm going to get a head or a tail. It is again, they are totally independent events, right? So knowledge of the random variable in the first trial will not give you any information about the occurrence of the event or the value taken by the random variable denoting the second trial. Those two random variables are uncorrelated. Okay, I hope you got the an overall idea of what correlation and uncorrelation means. Okay, with that, yes, I think there's a question.
So uncorrelated and independent are the same?
No, they are not the same. There is a subtle difference, but in general, if you remember last class, we were talking about jointly Gaussian random variables, right? For them, both are same. Maybe I will just give you the result, but I will not discuss more on that. The result is okay. I will just it's a very good question. It's a very subtle point. Not many knows that, but that is the true that they both are different notions. subtle point. If X and Y are independent, it implies that X and Y are uncorrelated. Okay, it implies. But if X and Y are uncorrelated, it does not imply that X and Y are independent. Okay, but okay, maybe I'll put a star here, some other symbol, $. But note that X and Y uncorrelated implies X and Y independent if only under one condition, if X and Y are jointly Gaussian. Okay, so the general answer for your question is no, they both are not equivalent. But one independence implies uncorrelatedness, but uncorrelatedness does not imply independence. But uncorrelatedness will imply independence if X and Y are jointly Gaussian. So for the purpose of this course, where you will be considering jointly Gaussian random variables, you can think that both are equivalent. But if they're not jointly Gaussian, they are not the same. Okay. I mean, there is some mathematics that is lying behind these concepts. That's why I'm not going in depth in these points. Okay.
Yeah. Jointly constant. Okay.
Yeah, these again. So my suggestion is go through today's lecture and then again go back to previous lectures notes and then go back and forth. Then you'll get a better understanding of everything.
Okay.
Yeah. Then measure of correlation. Now we have defined what correlation is. We have intuitively, physically, we have understood what it means to be two random variables to be correlated. But how do you mathematically characterize it? Precisely by the notion of covariance of X and Y. It's defined as expected value of X minus mu X into Y minus mu Y, conjugate. Okay, or in other words, it's like more concrete version to define correlation between two random variables is by rho, that is called the correlation coefficient. Is defined as the covariance of X and Y divided by sigma X sigma Y, that is the square root of variances of the product of variances of the two random variables X and Y. Okay, it's a property that fact the absolute value of the correlation between X and Y, okay, is less than or equal to 1 if rho of X comma Y mod is equal to 1, implies that X and Y are perfectly correlated. Means if I know what is the value of X, that is the value assumed by the random variable X, with definitely deterministically I can tell you what is the value that the Y random variable will assume. That is called perfect correlation. If rho of XY equal to 0, this implies that X and Y are uncorrelated. That is, if I know what is the value that is taken by random variable X, in no way I can guarantee that the random variable Y will take some particular value. I cannot comment. Then that is the uncorrelated value. Any number which is less than 0, which is more than 0 and less than 1 is correlated. With some guarantee you can tell that, okay, if I know what is the value of X, I can, with some guarantee I can tell what is the value of Y that Y will assume. Some guarantee. Okay, so now we will solve a question related to, basically this is a modified version of previous year assignment question. Okay, let the random variable X, it's a random vector, okay, random vector X is equal to X1, X2 and so on till X10. Okay, it's a 10-dimensional vector. It's a transpose. The C in 10 cross 1 be a random vector. Then define another vector y is equal to 1, 2, and so on till 10. Be a 10-dimensional vector. See, it's a y vector is a deterministic vector. It just says the vector is comprising of values 1 to 10. So if you remember, the random vector has these 10 random variables. Let each of these random variables xi be Gaussian with 0 and sigma I square. That is, the ith random variable is Gaussian distributed with mean 0 and variance sigma I square. And xi's are independent. That is, all these random variables are independent of each other. Okay. Then find number 1 mean of z, which is defined as y transpose x. See, y transpose is 1 cross 10. X is 10 cross 1. So what is y transpose? It's a 1 cross 1. So z is a scalar. Okay. So z is a random variable. It's not a random vector. I'm asking what is the mean of this random variable. Okay. Second question, the variance of z. That is, what is this variance of the random variable z, which is same as y transpose x. Okay. So we will now systematically solve it. Answer. So first one is mean of z, right? That is expected value of z. Is nothing but expectation of y transpose x, which is same as expected value of what is y, 1, 2, and so on till 10. Y transpose, it's a row vector. X is a column vector, x1, and so on till x10. This one, right? This is nothing but, you can see, this is nothing but expectation of summation of I is equal to 1 to 10, I into xi. Is this clear? I've just did the multiplication of this column row vector and the column vector. Now, this is same as summation over I equal to 1 to 10, expected value of I into xi. This is because linearity of expectation. I have told this in the last time also. If you take the sum of two random variables and take the expectation, that is same as taking the expectation of both the random variables and then adding them up. Okay, this is equal to summation over I is equal to 1 to 10, I into expected value of xi. Because if you fix a particular running variable I, this I is a deterministic number. It's nothing like random. Only xi is random. So deterministic expectation of any deterministic number, there's no meaning. Just bring that as a outside. There's expectation of a constant is a constant, the same constant itself. Okay, but what is this expectation of xi? I told xi is a normal 0, sigma square. So this is equal to 0. That means summation over I into 0 is equal to 0 itself. The mean of the random variable z is nothing but 0. Is this clear? Okay, I hope it's clear. The next is a variance. Okay, z is nothing but variance of, I'm just writing what z is. Z is nothing but sum over I is equal to 1 to 10, I into xi. Okay. This is same as, okay, this is another property that you can remember. The property is, if a1 and so on till an, that are n random variables, are independent, okay, then you can show that the variance of their sum is same as the sum of their variances. It's correct only under the condition that these random variables and random variables are independent of each other. Okay. Now in the given question, I told all these x's are independent of each other. So I can come from this step to this step. Is this clear? Okay, I hope it's clear. Now, I is again a constant. Okay. Can anyone tell me I want to bring I outside the variance? So what will I become? Is this correct? Can anyone tell me if this is correct?
Yes.
Well, it won't be right, because what I told, if you scale a random variable by a constant, then the variance will be scaled by the square of by the constant square times variance of xi. So variance of I xi is same as I square times variance of xi. Do you agree with this now?
Yes, I wanted to tell that. Yes, I square.
Yeah, correct. Then you're right. So that's why I square times variance of xi. But what is variance of xi?
Sigma square.
Sigma I square. I told
Sigma I square. Yeah, sigma.
Yes, correct. That's why I square into sigma I square. Variance of that. Okay. So the mean is given by 0, and the variance is given by summation of I is equal to 1 to 10 I square times sigma I square. If sigma 1 equal to sigma 2 and so on till sigma 10 all are same equal to, let's say, sigma, then what is this? Summation over I equal to 1 to 10 I square into sigma square is same as sigma square into summation over I is equal to 1 to 10 I square, which is nothing but sum of the squares of first 10 natural numbers. You can show that this will turn out to be 385 sigma square. Okay, that's just the mathematics, some algebraic manipulations. So this is how I think this was there in one of the assignment questions, but I've modified the question slightly. But this is the way to compute the mean and variances of some operation on random variables. Okay, so we have come far from the start. So it's 7:37 now. We will now switch gears and we will now go back to eigenvalues, eigenvectors. So if there are any more questions on the notion of random variables and Gaussian random variables, correlatedness, some more problems, please let me know so that the next class I can come up with some more materials for you people. Okay. So now we will now switch gear and talk about eigenvalues and eigenvectors of square matrices. Okay. So just to recollect, let A in C to the n by n be a square matrix. Okay. Then lambda is an eigenvalue. So eval is a short form for eigenvalue of A, with x is a complex n by 1 vector, C to the n, which is other than a zero vector. X is a non-zero vector. Is the corresponding evec. Eigenvector is denoted shortly, I will call it as evec of A if Ax equal to lambda x. Okay. This is called as eigenvalue equation. Okay. This doublet lambda comma x is called an eigenpair of A. Okay, this is something very familiar to all of us. Now, very important aspect of this particular eigenvalue and eigenvector is what is called the characteristic polynomial. It's defined for a matrix for lambda in complex number C and A in C to the n by n. The polynomial PA of lambda defined as the determinant of A minus lambda I. This, if you expand the determinant, you can show that this is of this form: C naught plus C1 lambda plus C2 lambda square and so on till Cn minus 1 lambda n minus 1 plus minus 1 power n minus 1 times lambda power n. Okay, this is nothing but a general polynomial of of nth degree in variable lambda, right? This polynomial where C naught, C1 and so on till Cn minus 1 all belongs to complex scalars is called the characteristic polynomial of A. In lambda, right? That is, this is a polynomial in lambda which is evaluated as the determinant of the matrix A minus lambda I. If you expand determinant A minus lambda I, you can show that this is our answer. Output will turn out to be a polynomial of this form. That polynomial is called characteristic polynomial. Now, result, it's maybe you can call it as a theorem or result or fact or however you want, but I'm just, for the mathematical accuracy, I'm calling it as a theorem. So lambda belongs to the complex C is an eigenvalue if and only if lambda is a root of PA of lambda equal to 0. This is called characteristic equation because I'm equating a polynomial to a number, it becomes an equation. Okay, so essentially what I'm trying to say is you compute the characteristic polynomial of the matrix A and find the roots of the polynomial equal to 0. Those roots are the eigenvalues of the matrix A. As simple as that. Okay, this is something we know from our previous classes. All right, and we also know that eigenvectors can be computed by finding vectors, maybe eigenvectors corresponding to eval lambda. Computed by finding the vectors in null space of A minus lambda I. This is something we saw in the last class and we stopped. Okay, so now if anyone has doubt in this particular result, please ask me, because this is very, very basic to eigenvector eigenvalue understanding. Okay, I will now solve a problem on how to do this, but if anyone has doubt in this statement, please let me know.
One question. So, is this characteristic polynomial always present for this equation of eigenvector and eigenvalue?
Yes. So characteristic polynomial is defined for a matrix. You can always find a characteristic polynomial for any matrix. And what I'm saying is, for this characteristic polynomial equal to 0, okay, that becomes an equation. If you find the roots of this equation, those roots will turn out to be the eigenvalues of the matrix A.
Okay, yeah. So this is a
did that clarify?
Yeah, so this is a method for calculation of the eigenvalues for a matrix.
Correct. That's what I'm leading to.
Okay, thank you.
Yeah. Okay. So one small notation I will introduce and then I will solve an example. It's called the set of all eigenvalues of A, the matrix A, is given by sigma of A, lambda 1, lambda 2, and so on to lambda n. For an n-dimensional matrix, nth order matrix, square matrix A, you collect all the eigenvalues lambda 1 to lambda n as a set and call this sigma of A. This is called the spectrum of the matrix A. If I call something a set as a spectrum of the matrix A, that means the set comprises of all the eigenvalues of the matrix A. This is just a notation. Okay. Now let's solve a quick example to find eigenvalues and eigenvectors. Okay, I'm going to give a recipe to how to do computation, and we will do that alongside with an example. Step 1. A. Okay. So what I'm saying is the first step, compute the eigenvalues by finding the roots of the characteristic equation. Okay, this is called the characteristic equation. Call these roots as the eigenvalues lambda 1 through lambda n. To compute the corresponding eigenvectors for every I from 1 to n, compute the matrix Bi equal to A minus lambda I times identity. And you need to find the basis vector of in the null space of the matrix Bi, or the null space of matrix A minus lambda I, which is same as what I told here. Okay, do that for every eigenvalue. All these vectors which you get from every iteration together constitute the eigenvectors corresponding to the eigenvalues lambda I. Okay, this is as simple as that. Okay, we'll do an example now. A equal to 4, 1, 2, 3. Step 1 is determinant of A minus lambda equal to 0. That is same as saying determinant of A minus lambda I, right? So means 4 minus lambda, 2, 1, 3 minus lambda equal to 0. Expand this, expand determinant 4 minus lambda into 3 minus lambda minus 2 equal to 0 implies 12 minus 7 lambda square plus lambda square minus 2 equal to 0. You can show that this is nothing but lambda minus 2 into lambda minus 5 equal to 0 or lambda equal to 2 comma 5. So for this 2 by 2 matrix, the eigenvalues are 2 and 5. Step 2. Compute the eigenvectors. First, let me consider lambda equal to 2. Compute the eigenvectors corresponding to the eigenvalue 2. The matrix B is nothing but A minus lambda into I, A minus 2I equal to, what is A? 4, 2, 1, 3. 4, 2, 1, 3 minus 2, 0, 0, 2. This is nothing but 2, 2, 1, 1. Now, find X in null space of B. Okay, that is, what does it mean? B times X should go to 0. That is the meaning of null space. Can anyone tell me one such value of x1, x2? Can anyone tell me one values of such vector x?
One minus one.
Yes.
Yes. Yeah. Very good. Yeah. 1 minus 1. That means I take the first column and subtract the second column. I get 0, all 0 vector. Because first and second columns are same. So 1 minus 1 is the valid solution for this particular equation. But it's not just 1 minus 1. Any number C multiplied by 1 minus 1, let's say 2 minus 2, 3 minus 3, any such solution, any such vector is a solution to this equation. So I can commonly write this as C times 1 and minus 1. And one of the eigenvectors for this lambda eigenvalue equal to 2 is 1 minus 1. Okay. Therefore, eigenspace, if you remember, that is what I defined the last class. Eigenspace is the collection of all eigenvectors for the given lambda, for the given eigenvalue. Is eigen denoted by E of lambda equal to is nothing but span of, that is the space spanned by this vector 1 minus 1, which is same as C times 1 minus 1 for all C in complex numbers. Okay, so 1 minus 1 is a valid eigenvector with the eigenvalue 2. Similarly, now lambda equal to 5. B equal to A minus 5I. Okay, that is same as 4, 2, 1, 3 minus 5, 0, 0, 5. Okay, this is same as minus 1, 2, 1, and minus 2. Okay, now X belongs to null space of B. Means what? Minus 1, 1, 2, minus 2 times x1, x2 equal to 0, 0. Now can anyone tell me the value of one such x which satisfies this equation?
2, 1.
Sorry, yeah, correct. 2, 1.
2.
Yeah, 2 times the first column plus 1 times the second column will give rise to the all 0 vector 0, 0. So 2, 1 is a valid eigenvector for the matrix A corresponding to the eigenvalue 5. Okay, corresponding to the eigenvalue 5. Therefore, E, that is eigenspace for corresponding to the eigenvalue lambda equal to 5 is nothing but span of the vector 2, 1, which is same as C times 2, 1, the collection of all vectors C times 2, 1, such that C belongs to complex C. Okay, Therefore, 2, 1 minus 1. See here, 2 and 1 minus 1 is the eigenvector. Similarly, 5 and 2, 1 is eigenvector. And 5, 2, 1 constitute the eigenpairs of A. Okay. Now, one very, very interesting example. It's a very interesting example. In fact, it's an astonishing example as well. Let the matrix A be equal to identity itself. Yeah, is there a question?
One doubt. In above
Yes.
examples, after the transformation of A, all the vectors are becoming 0, right?
Correct.
So then still we saying this all the x vectors are eigenvectors.
But you see, it is not A times x0. It is some other matrix B times x0, where B is defined as A minus lambda I. It's not Ax equal to 0. It's A minus lambda I whole times x equal to 0. That is different from Ax equal to 0, right?
Okay, this is B vector.
In
Okay.
fact, yeah. So if you see, B times x is equal to 0 is same as saying A minus lambda I times x equal to 0. This is same as saying Ax minus x equal to lambda x equal to 0. That is nothing but Ax equal to lambda x, which is the definition of our eigenvector eigenvalue.
Okay. Thank you. Sorry.
Yeah. Okay. So another very, very interesting example. What if the actual matrix A is an identity matrix itself? Now let's try to compute the eigenvalues and eigenvectors of this matrix. It's a very interesting example. Okay. So let's do the step. Okay, first step is to compute the eigenvalues. That is determinant of A minus lambda I equal to 0. 1, 0, 0, 1. Excuse me. Lambda 0, 0, lambda equal to 0. 1 minus lambda 0, 0, 1 minus lambda equal to 0. Implies 1 minus lambda square equal to 0 or lambda equal to 1, 1. There are two roots which are repeated roots, 1, 1. Okay. So for any identity matrix, all eigenvalues are same. So for example, if this were a 3 by 3 matrix, I would have got 1 minus lambda cube equal to 0, which means lambda is equal to 1, 1, 1. So eigenvalue of any identity matrix is equal to all repeated values equal to 1 itself. And how many times it repeats is equal to now the order of the matrix which you are considering. Here it's a 2 by 2 matrix. So you get 2 repeated eigenvalues equal to 1. Now step 2. Okay. Step 2 is little interesting. So I have now to compute for lambda equal to 1 only, because I have only one distinct eigenvalue, lambda equal to 1. For one lambda equal to 1, I need to compute the eigenvectors. What is B equal to? A minus lambda I. Lambda equal to 1, so this is nothing but A minus I. But A itself is equal to I. So I minus I is equal to what is this? So null matrix. So all the matrix with all zeros. So now I'm saying X belongs to null space of B. Now can anyone tell me what X will satisfy Bx equal to 0?
Zero. It should be 0.
Really? See, B I'm saying all zero matrix. What X will satisfy Bx equal to 0?
Any value of x.
Exactly. Any X is a solution. but with a caveat that x cannot be a zero vector, because an eigenvector by definition cannot be a full all zero vector, right? Therefore, any non-zero vector is an eigenvector of an identity matrix. It's a very, very interesting result. Maybe now it's difficult to visualize why it's interesting, but at least it should be surprising to most of you. But why it's interesting may not be very clear. But when you go into geometrical interpretations of eigenvectors and specifically the something called singular value decomposition, which professor will describe in few classes. When you go to geometrical interpretation, you can very well appreciate what does this particular fact mean? What does it mean that an an identity matrix has any non-zero vector as an eigenvector? Okay, these are very interesting properties. But yeah, this is what I have. So I have actually a couple more results to discuss. But in the interest of time, maybe I can start my next session with those two results. Okay, so I'll stop now with here. If there are any questions, we can continue. Or we can meet next week again.